The aim of our project was to design and construct a maglev demonstrator that could be used to showcase the technology behind magnetic levitation transportation. The main objectives were to achieve levitation, propulsion, and finally, speed control. Our motivation is to use the final product in schools and university fairs to educate people on the operational principles and environmental benefits of maglev. The initial design of the track, in CAD, was to have an outer and inner ring with a track selection element. Later, this was changed to a simpler loop to reduce complexity, and so every track piece was the same. The first train design was straight, with slots to house button magnets for levitation. These turned out to be too strong, so magnetic tape with poles striped along the length were used instead. After a few train iterations, the design process concluded with a train that had a rounded profile to fit the radius of the track, and with two button magnets in the middle to act as the secondary for the linear motor. Once the final train design was printed with a tight fit on the sides, the magnetic strips maintained a steady levitation, even when knocked from above. Afterwards, various weights were added to the train and the air gap was measured to understand more about the magnetic forces. The smaller the air gap, the less likely the train is to bobble around the track, so it will be more controlled. The train, with its heavy button magnets placed in, was now able to move easily with little friction around the bends of the track. For propulsion, a magnetic force is generated by sending 600 mA of current through two coils in series. This attracts the train to the linear motor, the current changes direction, and repels the train along the track. This was tested by building a Lego car mounted with a magnet. To control the train, a light gate had to be made using LEDs and LDRs. The LEDs would be placed on the edge of the track, with the LDRs facing them. When the train passed over the LEDs, the resistance of the LDR would increase. The voltage across the LDR would also increase, and the Arduino microcontroller would read the length of time that this change was measured. The velocity of the train could be instantly calculated before the train moved over the magnets. This velocity was used to perform two separate functions: calculate the period of the signal sent to the coils, and the required acceleration to meet the desired velocity. The acceleration of the train was limited to 0.1 meters per second squared, to ensure that the current through the coils wouldn't cause any overheating. The calculated acceleration was converted into a current error to be used in the PID loop. The correcting current was then used to calculate a voltage output between 0 and 5 volts, which is the range of the PWM control in an Arduino microcontroller. This allows us to see the time it takes to reach a desired velocity, displacement, and current. What makes this design unique is that it's transportable, modular, and easy to use. The hope for the Modulev system is to bring maglev more into the public eye to demonstrate and educate people on the benefits of this levitating method of transportation.